So let's say you give this diagram here of a mass attached to a spring, and the question says, find the energy diagram for the system above, where the spring exerts a force of F equal to negative kx on the mass. To start, what is an energy diagram? An energy diagram shows both the potential energy, U of x, and the energy of the object subject to the force corresponding to U of x. So basically, this just means that an energy diagram plots the potential energy of the system as a function of displacement. And we know that the force of a spring is equal to negative kx, and we also know that force in general is equal to the negative derivative of the potential energy. We need U of x, and we can use this equation here to find U of x by first multiplying both sides by d of x, and then we can multiply both sides by -1 to get rid of the negative signs. From here, we can integrate both sides from points x equals 0 to an arbitrary point x. If we do that, the bounds of integrations can be written as so. We can start by first integrating the left term, which if we do that, we get this, and then we can integrate the right term, and if we do that, we get this. So we can plug these both in, and then we get this answer here for the potential energy of the system. We can start establishing our energy diagram by first noticing the total displacement. The system goes from -a to a, so that's going to be our total displacement for the system. And on the y-axis, we're going to have the potential. And so we can first start by looking at what the potential energy is going to be at -a. We can plug this into our potential energy equation, and if we do that, we get ka squared over 2, which is also just equal to u at a. The potential energy at both these end limits are the same. Then we can also plug in x equals 0, and if we do that, the potential energy at 0 is equal to 0. So from here, we can draw a general shape for the graph. We can note that the total mechanical energy of the system is constant. E is equal to u plus k. Bound limits -a and a. The energy is going to be equal to the potential energy, which is equal to ka squared over 2. So that's the total energy of the system. Now, if you take a random point on the graph here, this boundary is going to be u of x, and this is always equal to e. But what is this question mark value here? Looking at these two bounds we identified, this is equal to e minus u of x. So what is this question mark distance? E minus u of x. We know that e is equal to u plus k. So if we bring u to the other side, e minus u is equal to k. So this is actually going to be equal to our kinetic energy of the system. So at any random point, the distance above the curve to the maximum is the kinetic energy, and the distance below the curve to the point is the potential energy. So we can note that k is largest at x equals 0, and this means that the velocity of the spring is greatest at position x equals 0. Additionally, at the potential maximum points, -a and a, the kinetic energy is 0. This means that the object's velocity is 0 at this point, because if we look at our diagram here, at -a, the potential energy is equal to ka squared over 2. We know that the maximum energy is equal to k squared over 2, so if we plug both these in, we find the kinetic energy is equal to 0. And we also know that the kinetic energy is equal to 1/2 mv squared. The kinetic energy is equal to 0, that means the velocity is also equal to 0. But what can we say about the force? We know force is equal to this, and this means that the force is equal to the negative of the slope of the graph. And so from 0 to a, the slope is positive. The slope being positive means that the force is negative. This makes sense because the force from the spring will be directed towards the equilibrium position because the spring is stretched. So from 0 to a, the force is negative, acting towards the equilibrium point. And then if we look at it from 0 to -a on the graph here, the slope is negative. And the slope being negative means that the force is positive. That means that it's also directed towards the x equals 0 position at this point. And this makes sense because the spring is compressed from 0 to -a. Therefore, we conclude that force is always directed towards the origin. And this makes sense because it's a restoring